So welcome everybody joining on YouTube. It's April 16th, and this is our second day of triangle trigonometry. So we have a warm-up that's been posted here, and we can see that what we're going to do is a lot with triangle trigonometry is trying to figure out different measurements for these geometric figures, specifically triangles, that we can use trigonometric functions to do. So right here we have, so the students that are here today have sort of worked through this problem, and then we'll go in and work through it and see what we got. So, Nick, what did you get for the first piece of this? What did you solve for first?
I actually wasn't thinking and did the sides first.
Okay, so on second thought, what would you have done first?
Well, and I don't think it really matters, but the second angle is easy to figure out because it's just 45 degrees.
Yeah, right. So there's a classic, right? It's a 45, 45, 90 triangle, right? So this is our isosceles right triangle. Think about it that way. Yeah, and so all the angles have to add up to 180. So that one's got to be 45. Yep. So I think that's the one I would do first, and then what we have to do is figure out, what number goes over here, what's this side length, and then what number is going to go over here, right? What this side length is. So we have to figure out our hypotenuse and our other side here. All right, so which one did you do first?
I did the opposite side.
Okay, so the blue one here. Okay. So as you're thinking about this, if this is our opposite side, right? So you call this opposite, which I'm guessing that this angle. So then this is the angle you call theta, right here, right? So down here in the bottom left is our angle theta. All right, so if that's theta, then that makes this our adjacent side. So what I need to do is I need to think about opposite and adjacent, right? So you had a trigonometric function that had opposite and adjacent.
Yeah, I used tangent.
Tangent, right? So we would have said, hey, tangent of 45 has to be equal to the length of our opposite side divided by 25. Okay. All right, so what was tangent of 45 degrees?
1.61977.
So you made a classic mistake, okay?
So I did. It's in radians.
Radians, right? Yeah. So if you have your calculator in radians, then that's not going to work out. So you got to put your calculator in degrees, and so I'm really happy that happened. So we can that's a really common error, and it can throw some confusion in there. So if it was in radians, if this measure was in radians, we'd want our calculator to be in radians, but it's not. It's in degrees. So tangent of 45 degrees is
1,
right? Yeah, so we would get 1 is equal to the length of our opposite side divided by 25. Right, so what I can do is then multiply by 25 on both sides, so I get the length of my opposite side has to be equal to 25. Right, so we can go ahead and replace this here, right? So what has to go over here is 25. Right, so this is probably something that is curious to the observer because this length is 25 and this length is 25. And I guess my question is that always going to happen? Right, so if this was something else, if this was like, 100, would this also be 100? If this was 7, would this also be 7? What do you think?
I think if it's an isosceles, then yes, because the angles are the same.
Yeah, right. So in the isosceles triangle, those two side lengths are the same, right? So this and this. So anytime you have this 45, 45, 90, you're going to have the base and the height are going to be the same. Yeah, so that's true. And if the base and the height are the same in a right triangle, then these angles have to be 45 degrees. Right? So it's one of these special triangles that we see pop up. So we get this. We get 25 on both sides. And then I guess the last thing we're going to do is we have to figure out what the hypotenuse is. Now, there's multiple approaches to this. So you could use Pythagorean theorem, or you could use, different trigonometries. If you wanted to, you could use sine, you could use cosine. Either one is going to be fine here. So Nick, what did you use?
I used a Pythagorean theorem.
All right, so Pythagorean theorem. So this says 25 squared plus 25 squared is the length of my hypotenuse squared. Right. Okay, so this is, we'll call this H. Now, one thing that's interesting here is I'm adding two of the same things together. So for me, I'm not going to use a calculator to solve this, right? So I could do it out and we could get a nice decimal and all that. But we can actually get a pretty quick result here. So 25 squared plus 25 squared, I'm adding the same thing to itself. So what this is really 2 times 25 squared is equal to H squared. Does that make sense?
Yeah, I think so.
Yeah, so I have two of the same object, right?
Yeah.
So if I had like 7 plus 7, that would be 2 times 7.
Mm-hmm.
So whatever 25 squared is, if I add it to itself, I'm going to get double, right? So I'll get 2 times that number. And so now what I can do is I can go ahead and take the square root of both sides here. And so on the right-hand side, I'm left with H. And on the left-hand side, what happens is I can take the square root of each of these pieces separately since it's a multiplication. So I can take the square root of 2 and I can take the square root of 25 squared. So the square root of 2, I'm not going to do a whole lot with that, but the square root of 25 squared is just 25. Right, so my hypotenuse, if I wanted the exact answer here, we could work through it reasonably quickly without a calculator, get the exact answer. And we can, oftentimes I write it like this, so 25 times the square root of 2. And so you will, you'll see this too, right? You'd see that square root of 2 come in if you were to use sine or cosine. Since sine and cosine of 45 degrees, I have square root of 2 over 2. Okay. So does this match up if you have your, it seems like you may have gotten your answer as a decimal, so did you match it up with 25?
Yeah, and it works.
It works, yeah. Yeah, so this is a nice example where we have a 45, 45, 90 triangle. And then if we recall, right, so if you go back to the video from Tuesday, we actually worked through this example where we did a 30, 60, 90 triangle. Right, so these are going to be common ones that you see pop up. But as I alluded to on Tuesday, those aren't the only things that we have, right? So you might have another triangle example that looks something like this, where we don't have such nice angles. Okay, so we're not going to be able to use our table to look up the sine or cosine of this 15 degrees. We haven't developed those. So this is an example where we're going to end up turning to the calculator to get some of our answers. So, all right, so let's think through this one again, right? So we have a 15 degrees and building on what we did on Tuesday, we've labeled our sides of this thing a little bit differently, right? So Nick, do you remember what the big change here was? Right, so we have this as our hypotenuse, okay? So it's across from our 90-degree angle. But in a lot of our other triangles, we were calling this bottom the adjacent and then this vertical side the opposite side.
Okay, yeah, because the angle's in a different spot that they give us.
That's right, yeah. So if I'm giving you this right here, 15 degrees is up here, the opposite side changes because it's always referencing where the angle is. So this is the side opposite your angle, and this would be the side adjacent to your angle. So when we go through and we use sine and cosine to figure out the different side lengths, we're going to have to keep that in mind. Okay. All right. So for me, step 1, I'm going to go ahead and figure out what this angle is. So do you know what's going to go down here in the bottom left hand?
75.
Yeah, 75, right? So you want to make sure all of these add up to 180, and then so you have to plug 75 in, right? You need 75 more degrees to make that angle of some add up to 180. Okay, so we get that piece of information. Often this is the quickest one. And now what we have to do is we have two more pieces of information we need to know. What is our adjacent side and what is our hypotenuse? Okay, so go ahead and erase this. So the text that's in white here is what was given to us, and then these other colors will represent what we're figuring out as we go along. So, so what do you think? You want to do adjacent or you want to do hypotenuse?
For me, I would think I would go for the adjacent just because I find the Pythagorean theorem easier to work with if you have the legs rather than the hypotenuse.
Okay, so you're going to go for the adjacent side first.
Mm-hmm.
So if you're going to do the adjacent side, what you're given, right, you're given this opposite. The opposite is 5, and then you need to know the adjacent. So those are the two pieces of information. So you have opposite and adjacent, and you have to come up and pick the right trig function that's going to relate the opposite side to the adjacent side. So for the benefit of those working at home, right, we think about, we're in the back of our minds, we're thinking about SOHCAHTOA still, and we want to go through and say, hey, which function relates the opposite side to the adjacent side? And so when I look at TOA here, that's the one that I'm going to pick out, right? So I'm given the opposite side, I'm looking for the adjacent side. So we're going to have this tangent function that's going to pop in for us, right? So we're going to say, to find the adjacent side, we're going to say, hey, tan of 15 degrees is equal to our opposite side divided by our adjacent, right? So we'll call this whatever the length of our adjacent side is, that's going to go in our denominator. And so before I even plug anything in, what I can do is I can multiply through by the length of my adjacent side, which we called ADJ here. And so I'll get whatever the length of my adjacent side times tangent of 15 degrees equals 5. And so the length of my adjacent side is 5 divided by the tangent of 15 degrees. Okay, so if we wanted to, if we weren't interested in the measurement of this thing, this could be our exact answer. But oftentimes we want to know, hey, what is the decimal approximation to this thing? So what we're going to do is we can jump over to Desmos. So I'm going to open up a Desmos window, and then we will jump over there. Okay, so you can see I'm in Desmos. All right, we'll jump into the graphing calculator. And what we want to do is we want to do 5 divided by the tangent of 15 degrees. And when I plug this into my calculator, I get something really funky, right? So it's telling me that, hey, the side length of your triangle should be negative 5.8. That doesn't feel so good to me, right? So negative side lengths feel pretty weird. So what happened?
Are you in radians?
Yeah, all right. So the graphing calculator defaults to radians. So what we're going to do is you go over here to this wrench, right, in graph settings, and then there's radians and degrees down at the bottom. So we'll go into degrees, right? So you can see when I click over to degrees, this number changes. If I'm in radians, it's negative 5.8. If I'm in degrees, it's 18.66, right? And so we can go ahead and record that number, right? So 18.66. And so just quickly using our calculator here. All right, so let's go back and then see what we had written down now. So I recorded our data. And so here's 18.66. All right. So Nick, now you said you wanted to use Pythagorean theorem to do something? Or do you want to talk me through it?
So it would take 5 squared plus 18.66 squared. And that comes out to 373.1956.
Okay. And what should all that be equal to?
That should be equal to the hypotenuse squared.
Yeah. Yeah, so what I'm going to do, so what you did is you computed the 5 squared and the 18.66 squared, and then you went and took the square root of that.
Yeah.
So what I'm going to do it all in one step. And so to avoid rounding errors as much as possible, I'm only going to plug one expression into the calculator instead of sort of rounding earlier and then doing some more stuff later. So what I'm going to do is I'm just going to take the square root of both sides of this. So what I get is I get the square root of 5 squared plus 18.66 squared. That is going to be the length of my hypotenuse. So what I'm going to do is I'm going to leave it just like this, and I'm going to plug this exactly as it looks here into Desmos. So no rounding or anything like that. I'm just going to plug this right in. Okay. So let's go ahead and jump back to our Desmos window. Okay, so what we wanted to do is we wanted to take the square root of 5 squared plus 18.66, right? This thing squared. Right, and so what we should see is it's about 19.32, something like that. Okay. One thing I want to caution here is like we already did round, right? So we already rounded this 18.66 here. So this is going to be pretty close, right? So if we only wanted it out to 1 or 2 decimal places, you're probably going to be okay. If you wanted to extend out further than that, right? If you really wanted to be super precise, you could, instead of 18.66, we could put this term in here, right? And you can see that these numbers down the end change a little bit, right? So our first couple numbers didn't change. It wasn't that level of precision, but this would be sort of our most accurate answer. So it just depends on sort of what you're doing with it. If you're dealing with things that are like need to be measured really to precise digits, so think like medical device manufacturing or hard drive computer part manufacturing, where you're dealing with like really, really tiny parts and things, you would need these numbers to be really precise. So at times you may need more precision than just like 2 decimal places. Now, that said, if you're talking about, if you're measuring things like a triangle, if you were doing like building your deck or something and you're measuring to the nearest inch or, nearest quarter inch, you probably don't need, you don't need 10 decimal places or anything. So again, it's all context dependent here. But in any case, right, so if we round off to 2 decimal places like we did before, we would say that this is 19.332. Okay. All right, so let's put that in there, 19.32. And then that's all of the missing pieces of information, right? So from this, what we were given initially, we had one angle, one side, and we knew that we had a right triangle, and we were able to go ahead and we were able to figure out the other 3 pieces of information, right? So one angle, one side, and then the assumption it's a right triangle. So in that sense, we're given 2 angles here. Then we were able to figure out all the information about this triangle, all the different side lengths and everything. Okay. So the last type of question that we might see is something that looks like this. Okay. So what happens in the case where, maybe we aren't given an angle, but we're given some side lengths, right? So what if I told you that we had a side length of 7 and 7 here, and then we had some angle theta that on the surface, I don't know what it is. Can we still, in this particular case, can we still go through and figure out what the other side length is and what the angles are? Right, so we have this question. Right, what is the hypotenuse, or what is the length of the hypotenuse? And then what's the measure of angle theta? So any ideas here?
Well, we could use the Pythagorean theorem to figure out the hypotenuse.
Okay, so you get 7 squared plus 7 squared is h squared. So very similar to what we did before. We have 2 times 7 squared is h squared. And so the square root of 2 times 7 is equal to h. Okay. All right, so we got that. And so what about the angle?
Well, just looking at the triangle, because both of the legs are equal, does that make it, that makes it an isosceles right triangle, so it's going to be 45, right?
Correct. All right, so in this particular case, we have a special triangle here. That's hint that I was right again. Yeah, so it's this isosceles right triangle, so you have as you said, these are the same, so our angles have to be 45 degrees, right? So this has to be 45 degrees, and then this one has to be 45 degrees. Right, so in this particular case, we didn't really have to do any computing. We just we recognized that we have a special triangle, and then we were able to put the angle measures in there. But this is the evolution of our next step in sort of figuring out measures of triangles. So what happens in the event that we're given, say, 2 side lengths, right? So if I'm given 2 side lengths and no angles other than the right one, can we figure out those angle measures, right? So what if this wasn't 7 and 7? What if it was like 7 and 4? What would we do then? Could we actually figure out what these angle measures are? What we're going to do is, let's flip back to our notes here. So again, these are our notes that are posted on Plato under activities. So what we just went through is we just went through section 7.1. And so now what we're doing is moving on to 7.2. We're going to try to figure out, hey, what are these angles, right? So let's see if we could do this a little bit more generally, right? So this exploration here, if you're exploring along at home, what could we do, right? So what could we do without knowing, right? So we already know that the answer to this angle, right? What is this angle measure here? We know that the answer is 45 degrees. But let's see if we can think through it in a different way that might help us when we don't know what the answer is ahead of time. So the first question that I ask here is, if I look at this triangle, if I have this angle right here, which function can I use? Can I use sine? Can I use cosine? Can I use tangent to come up with a relationship between theta, 7, and 7?
Tangent.
Yeah, so this is tangent, right? So what we're going to do is we're going to set up an equation, and then we're going to think about, hey, how do I use functions to solve that equation? All right, so let's jump back over to our blackboard. Right, so if I have this angle theta, what I'm seeing is we should have this relationship, right? So we should have a relationship that says, hey, tangent of theta is equal to 7 over 7, or we have this tangent of theta is equal to 1. Okay. So how do we solve equations that look like this? Do we know?
Don't we have to use like the inverse of tan?
That's right. So we're going to use the inverse of tan, which we call arctan. All right. So if you remember this, so we're going to see we have this function arctan. So tangent of theta equals 1 if and only if, right? So this is the same thing as saying that theta has to be the arctangent of 1, right? So theta has to be arctan of 1. And so what we can do is, in order to figure out this value, arctan of 1, we can go ahead and bring up Desmos again, right? So we could sort of use our tables, but let's bring up Desmos, our Desmos value, and then Desmos understands what the arctangent function is, right? So if I just type in arctan of 1, it's going to tell me that the answer to this is 45 degrees, right? So again, we're in degree measure, right? So if I put this in radians, it's going to give me the radian measure of the angle, and so this is pi over 4, and then a lot of the time the degree measure makes more sense to us, right? So arctan of 1 is 45. Okay, so so with that general process, right, if we set up our trig function, we can go ahead and then use the inverse trig function to solve some of these problems, right? So you can use arctan, arcsine, and arccosine as the inverse trigonometric functions. Okay, so here's 4 examples. So we'll go ahead and see if we can tackle some of these and see how we do. Okay, so we have somebody just joined us. So welcome, and then so we're working through our triangle trigonometry right now, and we're going to try to flip things a little bit on their head. So we're going to see that now that we have 2 side lengths, can we go ahead and figure out the angle measures? All right, so I'm going to give you all a minute to think through these, and then we'll come back together. All right, so we had some time to think about these questions. So what we're going to do is jump back over to our Blackboard and then think through these, right? So the general prompt here for all of these is what we want to do is determine the missing angle and side measures. So previously, our examples we were looking at, we were given an angle measure and a side length. And so now we're flipping that around. We're giving you 2 side lengths and seeing if we can figure out the other pieces of information that are in here. Okay, so what would you all do first, right? So if you're given this problem, in this case, like in the case before, what we were doing was we were determining the angle measure first. And you could do that in this case as well, but was there something that either of you decided to do first?
I found the missing side.
The side, yeah. Yeah, I think I would do the same in this case, right? So find those missing side lengths first. So how did you do it, Carrie? Did you Pythagorean theorem it?
I did 5 squared minus 10 squared.
Yeah, right. So if this is our missing side length x right here, you did. So let me go from the start here, right? So Pythagorean theorem says 5 squared plus x squared is equal to 10 squared. Then you subtracted over.
Mm-hmm.
You said, so what you said was x squared is equal to 10 squared minus 5 squared.
Yes.
Okay, so that would tell me that 10 squared is 100 minus 25. So on the right-hand side, I get 75. And if I take the square root of that, x would be the square root of 75. that what you got?
Yeah.
Okay, so this one over here, this is square root of 75. And then now we have to go through and we have to figure out what our angle measures are. So what was your approach to this? Did you find theta first or beta? And then how did you do it?
I found theta.
So the theta is this one down here.
Yeah, I found that one first.
Okay, and how did you do it?
I did cosine theta equals 5/10. Then I did arc cosine theta equals 5/10.
Yeah, right. So theta is arc cosine. There's another c in here of 5/10, right?
Mm-hmm.
Okay, and what was that? Arc cosine of 5/10 gave you
60.
60, right? So this would be 60 degrees if you put your calculator in degrees, right? So then this one right here, this would be 60 degrees. And how did you figure out beta?
Just added 90 and 60.
Yeah, so you didn't use trigonometry anymore. Now you went back to the angle sum is 180.
Yeah.
And so this had to be 30 degrees, right? Yep. So that's exactly right. So in these, there is going to be a point where you are going to have to use the inverse trig functions to solve for some of these angles, but you don't have to do it twice, right? So if this is something that is comfortable for you, you could absolutely use this to find beta, right? You could have done, arc sine, if you thought about it that way, but I think a lot of the time just adding them up is the easier approach. Okay, so here is example 2. We have a 9 and a 7, right? So this one is very similar to the last. So the only thing with this one that's different is our angle measures don't work out to be so nice. Like these are 60 and 90. So in the interest of time, I'm going to go ahead and skip this one, but move to a different one where instead of given the hypotenuse and the base, what we're going to be seeing is what happens if we have the two bases of the triangle, right? So this 8 and 3, we're not given the hypotenuse, and let's see if that changes anything for us. Okay, so Carrie, I'm going to take your approach just like we did before, and I'm going to find the hypotenuse of this first. So we would get 3 squared plus 8 squared is equal to h squared. So this is 9 plus 64, it looks like, right? So 3 squared is 9, a squared is 64. If I add those together, I get 73 is h squared. And then I'll just take the square root of both sides, which gives me h is square root of 73. Right, so far so good there. And so Carrie, last time you chose arc cosine, would you choose arc cosine again in this case, or would you choose arc sine or arc tangent? Does it matter?
I would probably do sine.
Arc sine. Okay. So Nick, what would you do? Did you pick a particular trig function that you wanted to use?
I would have used if solving for theta, I would have used tangent, so I don't have to use the square root.
Okay. So you would. So Carrie, are you solving for this one as well?
I don't have to. Do you want me to?
No, we could solve for beta, right? So I'm just asking, when you solved it, when you chose sine, did you solve for theta or beta?
Oh no, I haven't done it yet. But after I said sine, I went back and I looked at it, and I would have chose tangent too.
Okay, because you have that, so you don't have to do the square root.
Yeah.
Okay.
Right after I said sine, I was like, nope, not sine.
Okay, well, since you said sine, let's go ahead and let's see what that would look like, and then let's do tangent, and let's see if we sort of get the same thing, right? So we're gonna solve for this one, right? So we're gonna solve for this theta. We're gonna use tangent. We'll also use sine and see what we get, right? So if using tangent, since that's the one you both picked, right? So tangent of theta is the opposite side, right? So the opposite in this case is going to be 8, and the adjacent is going to be 3. And so theta here should be the arctangent of 8/3, right? So we can use that one, which is fine. And then let's go ahead and do it a different way. Let's do it in blue. Let's do it for sine, right? So alternatively, you may have chosen sine of theta. And so that's opposite over hypotenuse. So you should get 8 over the square root of 73. In which case theta is the arc sine of 8 over the square root of 73. All right, so looking at these, to me, on the surface, they look different, right? So is theta equal to this, or is theta equal to this? So let's go to Desmos and see sort of, let's turn these into decimal approximations and then see what happens, okay? So hopefully we can cross our fingers and say that these are gonna be the same. Oh, we'll find out, right? So our values here were arc sine of 8 over 3.
No, it was arctan, I think, of 8 over 3.
You're right, arctan. Right, so my angle is 69.44, and then arc sine of 8 over square root of 73. You can see that, hey, they do actually give me the same thing, right? So this angle is 69.44, right? If we want to round it off that way. And then we could go through and just, either add up, or we could, use trigonometry again if we wanted to do that. So let's put our value in here. All right, we'll go ahead and erase this. So we go, right, so this is 69.44. And then if we want to figure out beta, what we can do is we can go ahead and think to ourselves, hey, what would I have to add to this to get to 90? And the answer to that is, this would be a 20.56, right? So you could do this, right? 90 minus 69.44, and you should get 20.56, right? So that's how you could compute the other angle there, right? And so these are all degree measures.
So I have a question.
Yep.
In the Desmos functions, there's like cosine to the negative first power is what it looks like, and sine to the negative first and whatever. That's the same. Is that the same as like arc sine and stuff?
Yes, it is. So let's go ahead and then show everybody what you're talking about. Okay, so when we go to Desmos, if we click on this, if you're on mobile, you can see this show keypad, or I'm on a browser right now. So when you hit show keypad, you can click over here on functions, and it will give you sort of a list of functions that you can use in Desmos, and then you can see that we have these buttons right here. So yeah, so I'm using arctan because this notation can sometimes be confusing as the reciprocal, right? So sometimes you get confused with, hey, tan inverse, right? So we would do 8 over 3. We can see that it gives the same information. But notationally, right, a negative exponent sometimes means in the denominator. Right, so that's how we were interpreting negative exponents. In this particular case, we are not. This is a sort of an abusive notation where we're thinking of this as the inverse notation, right? So -1 on a function often means the inverse of that particular function. So yes, this is the same as this, but notationally, my preference is to write arctan to avoid that that confusion with negative exponents.
Okay.
Okay, so here we have inverse tangent is the same as arctangent. And so if you prefer this, if you want to use this, or if it's easier to just hit the function button, you're absolutely right. You can do that.
I also have a question.
Yes.
So before I realized we had Zoom going on, I was trying to do web work. And question number 3 asks for sine A, cosine A, and tangent A. Wouldn't those all be the same if you already find the angle to A?
No, right? So if you have the angle, the sine of the angle, the cosine of the angle, and tangent angle all could be different, right? But if you know what angle A is, you could certainly compute those. But if you don't, then you might have to figure out based on the sides of the triangle. So let me bring up web work here. So can you all see this? I'll pause here. All right, so you can see web work now?
Mm-hmm.
No, I can't see it on your thing.
You can't see web work?
No.
I can.
You can see my web work?
Oh, wait, here we go. I got it.
You got it? Okay.
Yeah.
So it's asking you for sine of A, sine of B, and sine of C.
Mm-hmm.
So what you have here is, so I use annotate to draw on this. The information that it's giving you is it's saying, suppose A is 5 and B is 12, right? So this is really, this side length here is 5 and this side length here is 12, right? So if we're filling this out.
I found everything else that I need. Like I found all the angles and all the sides.
So you actually don't need, that's more information than you need. So if you wanted to compute sine of A here, right? So we know sine of A is the opposite side divided by the hypotenuse. So it should be 5 divided by whatever you found for C, right? And so I believe in this case, you probably found this to be 13.
Yeah.
Right? So sine of A should be 5 over 13, right? So what you can do down here is you can use SOHCAHTOA to figure these out.
Okay.
Right. So if you already knew the angle, right? So if you determined what A is, then you could just plug it into the different functions and figure those out. But you could also do it as the ratio of the sides.
All right. That's all I was confused on.
Okay. But that, so far so good?
Yes.
Okay. All right. So it seems like, at least for the people here, that this stuff where we're given 2 side lengths and, figuring out the different pieces of the triangle, that feels pretty good to us.
Yeah.
Yeah. Okay. So the sort of next piece of this is, right. So how do we bring these things into context, right? So before, I'm giving you sort of these abstract triangles, right? So we're just sort of drawing a triangle. We're trying to figure out the side lengths. But this is actually really quite useful stuff, right? So if you're doing any sort of construction or measuring, trying to measure angles or grades in the road, or just trying to figure out, hey, I'm trying to build some steps here, what kind of measurements do I want to do? So I do a little bit of sort of home improvement type stuff, and so I'll have to build stuff outside for my deck, or if I built a ramp, for my dog. So I actually use these things to figure out, hey, what should my side lengths be, and sort of, what kind of angle do I want my ramp to have so that it won't be too steep for my dog to walk up. So these are all sorts of things that I have thought about and used trigonometry for. So this whole section right here, these are modeling problems. So we're going to go through and we'll think about these. And so the last 4 or 5 problems on the web work have to do with stuff like this, where we're giving you some sort of context, and then we want to make some sense out of it, find our triangle that's in there somewhere, and then sort of turn it into one of these more abstract problems. Okay. in this context, you often see these problems stated this way, where you have some sort of ladder leaning against a wall. So what I'll do is I'll sort of talk through this one to start, and this is a case where I wish I had a way to do side by side, but unfortunately, I'm not sure how to do that right at the moment. But so let's see if we'll read it, and then I'll just sort of restate it if you can, right? So it'd be helpful if you could bring this up as well somewhere, and then but I'll flip back if we have to. So 12-foot ladder is going to be against a wall, and the distance between the base of the ladder, so the part that's on the ground, and the wall is 5 feet. The question is, right, how far up are you going to hit the wall, right? So this classic type of problem, what we're going to do is we're going to think about it and say, all right, the first thing that I want to do is draw myself a picture. Okay, so let's jump back over to the Blackboard so I can do some drawing here. So draw yourself a picture, and then we're going to organize some information. All right, so we have a wall, right? So see my grand artistic ability here, right? So we have we have some sort of wall. Maybe it's made out of bricks or something like that, right? So you've got a wall, and you've got the ground, right? So here's your ground, right? So you have this ground here, and then what we would like to do is we're going to have a ladder that's leaning up against said wall, right? So you have a ladder that's something like this, right? So when I draw in a picture, you can imagine like, hey, I have this ladder leaning up against the wall, and the information that's given to us is that the base of the ladder is 5 feet away from the wall. So this length is 5 feet, and the length of the ladder is 12 feet. And the question is, how high up, right? What would this distance be right here? How high up on the wall would it hit? And so what we want to do when we set up these pictures is we want to pick out our triangle, right? So what I'm noticing here is that I have this, I sort of have this triangle that's in here. And if I turn this into an abstract diagram, like we had before, right, we're going to assume that this wall is sturdy. It goes straight up off the ground. And so my ladder would be something like this. And then the base, the distance away from the wall is 5. And the question is, well, how high up does it go, right? So we want to figure out this distance, right? So with any of these modeling problems, I'm sort of walking through this thought process as we go along, right? So I'm trying to read all the information. I like to draw myself a picture. It doesn't have to be sort of, with different colors, or you don't have to do anything crazy, but you can organize your information, and then from that try to extract one of these sort of more abstract triangles that we were using before. Okay, so in this particular case, I would use Pythagorean theorem, right? So we can call this x. So you get 5 squared plus x squared is equal to 12 squared. And so you get x squared is, 12 squared is 144 minus 25. Right, so x squared is 119. And so x is going to be the square root of 119, right? So what's going to happen here is this is going to be your exact answer, square root of 119. And if you're sort of playing along at home, this is probably not the most useful piece of information that you could give to somebody. But what you'd probably say is, hey, it's going to go up about 10.9 feet. All right, so if we were to go ahead and plug in the square root of 119 into the calculator, you get about 10.9. And what we'd expect is a 12-foot ladder will reach up on the wall about 10.9 feet. Okay, so this is sort of our general process that we walk through. Draw a picture, try to get this abstract triangle out of it, and then do whatever necessary calculations there are whether that's finding the angle or finding the missing side lengths or whatever information is being asked or whatever information that you want. Okay. So Carrie, Nick, was that pretty good for you?
Yeah.
Yeah. Okay. So let's go ahead and I'll give you the opportunity to try out this one here. All right. So number 2 is a little bit different. All right, so we've been thinking about this, and while you and I have been drawing a picture. Okay, so you might have something that looks like this. Okay, so as the problem is stated, what we have is you have a wire, and then you're going to have it at the top of a building. You're going to stretch it all the way to the ground. And what we're going to see is that the wire, it's going to touch the ground 50 feet away from the building. And you can take out your protractor and you actually measure that angle and find that the angle is 30 degrees. All right, so what we're going to do is figure out how we can use trigonometry to determine the height of the building. And so one of the secrets here that we are not going to get to do is in past semesters, during this lesson, when we would do this in class, we would all go outside because it's springtime. We'd go outside and we would actually do this. We could actually, I have an activity built where we can actually figure out the height of Wilson Hall. And so you're going to use similar principles here. But okay, so did you all set up a diagram that looks something similar to this here?
Yes.
Yeah, and so what did you get for the height of the building?
Oh, I haven't done that one yet.
Okay, Nick, did you get an answer, or do we need another minute?
Yeah. I got around 29 feet.
29 feet. Okay, so what was your computations? What did you do?
So I said tan of 30 is the opposite, or the height over 50.
Okay.
And then
you keep going.
yeah, and then the tan of 30, I just took that and multiplied it by 50.
And then you got
28.87-ish.
28.87. Okay. So our numbers, when we actually measure Wilson Hall, they work out to be a little bit different than this. But yeah, so this would be right. So we would take tangent of 30 degrees. and multiply by our 50 feet. And so what we're able to do is, you know, if I can't, maybe I can't measure this height, right? Maybe that's hard for me to do. But if I can, right? So if I can sort of measure this distance in some sort of angle, then we're able to do this. So when we do this in person, what actually happens is we don't measure this blue line. What we do is we use a line of sight. So we have people sort of stand out there like this, right? And so then another person, you know, what you would do is you would look from here, right? So you would look from here and try to do a line of sight from a point on the ground up to the building, right? So what you're going to do is you're going to sort of, you can hold a string, right, on somebody's head, and you could sort of use your line of sight to measure that, you know, that angle. So you'd have a piece of string, and what you can actually do is then take a protractor and measure this. So just using some trigonometry, a piece of string, and a protractor, we can actually measure the height of buildings, right? So measuring distances along the ground are pretty easy, right? So you can use a tape measure. Measuring heights of buildings are significantly more challenging, right? So especially if you can't get up to the top of the building, but still, just using some of these measurements, you can go through. You can measure the height of basically anything, right? You can measure height of trees or buildings or whatever, just with a little bit of trigonometry. So again, I think it's another cool application here. Okay, this one still feels pretty good.
Mm-hmm.
All right, so let's go ahead and let's see what is next up. All right. So some of the things that you might ask yourself are, hey, when I lean a ladder against a wall, right, like we did in question 1, we could ask how high it goes up. But another question might be, hey, I want that ladder to be sturdy, right? So when I put the ladder against the wall, I want to make sure that, you know, it's not going to sort of tip back on me, right? So if you put a ladder against the wall, if it's sort of too steep, you might, you know, the ladder might fall back like this. You want to make sure that, you know, you have a good angle here that's going to be solidly against a wall. And so what we're given, the information we're given here is the ladder will be sturdy if the angle it makes between, if the angle the ladder makes with the wall is somewhere between pi over 12 and pi over 6. Okay, and so if you want to convert that to degrees, that's somewhere between 15 and 30 degrees. Right, so I don't know, a way to think about that, so I don't know if I can use some sort of diagram here, but so if you have a ladder, let's see if I can do this, you have a ladder leaning against a wall, if it's sort of too vertical, right, then the ladder might tip back, and if it's too horizontal, the ladder will sort of fall down this way. So we want to get that right measurement there, right? So we're saying, hey, somewhere between 15 and 30 degrees, or somewhere between pi over 12 and pi over 6 radians. That will make it sturdy. And then, you know, and then under this new constraint that it's sturdy, the question is, how high up a wall could we make? So let's go ahead and think about this for a moment. I'll draw a picture here again. Okay, so get something that looks like this. Okay, so you have a similar problem to before, but we want, right? We're not given the length of the base anymore, right? We're given this sort of constraint that that our angle is going to be somewhere between pi over 12 and pi over 6. So here's a question I have for both of you. If this angle, right, if I make this angle bigger, is my ladder going to go lower on the wall, or is it going to go higher on the wall? Right, so if this angle is bigger, does it go down or up?
If the angle is bigger, then the ladder will go down on the wall.
That's right. So you can think about it this way, right? So if my ladder is up like this, right, versus if my ladder is down lower like this, right? So if we have sort of these pictures, this would be when we have a small angle, right? This would be when we have a large angle there, right? So if I have a smaller angle, that ladder is going to be higher up on the wall. So in this case, we want it to be sturdy, right? So we have to have this range. We have somewhere between pi over 12 and pi over 6, but which one are we going to choose? So which one's bigger? Pi over 12 or pi over 6?
Pi over 6.
Yeah, right. So this is bigger, right? So we actually want to choose this angle, right? So if we think about it this way, this is 15 degrees and this is 30 degrees. I think about it that way. So what we want over here is we want to make this angle to be pi over 12, right? So that's as small as we can make it while it's still sturdy, right? Or you can think about it in degrees. And so if now that we've drawn these pictures, we've sort of made some sense out of this problem, I can go ahead and then extract my triangle, right, that I'm given here. And so what we have is that this angle is 15 degrees, this is 10, and the question is, what is the height, right? If I have a 10-foot ladder and I can go, the best I can do is 15 degrees there. So how high up will I actually be able to reach with a 10-foot ladder, right? So a 10-foot ladder is not going to reach up 10 feet because that means the ladder would smack against the wall, but we would have something else. So looking at this triangle, solving for x, for me, what I would do is I would use a cosine. Right, so again, right, so this would be our adjacent side, and then this would be our hypotenuse, right? So thinking about SOHCAHTOA, this would be a cosine problem, right? So you'd get cosine of 15 degrees is equal to my adjacent side divided by my hypotenuse. So x should be 10 times cosine of 15 degrees, right? And then I'll just quickly put that into Desmos. So what we get is 9.66. Right, if we want to interpret this, right? So the ladder, for it to be sturdy, it would reach up the wall about 9.66 feet. And so with a 10-foot ladder, you can't reach 10 feet, but just over 9.5 feet, you can reach up that wall. Okay. All right, so we're not gonna do any more problems today. I'm gonna stop it here, but I'll kick it over to you for a minute if you have any questions about this or anything else.
I think I'm good. Thank you.
All right.
Yeah, I'm good too.
All right. So next Tuesday we'll do a couple more modeling problems, and then what we'll do is we will start to move into looking at how we can define rotations with these triangle relationships, and that will help us with our Desmos project. So if you want to get ahead, right, if you want to think about being on pace, maybe a little bit ahead, if you find a picture that you want to trace and think about a piece of it that you want to move, right? So we saw last time, if you want like a hands to wave, or if you want something to spin, right? So some students in the past have done things like windmills, or you could imagine a bow tie spinning or something. I'm sure you can come up with something clever. But something that you want to spin or move, and then we'll see, that will help you out if you already have that traced, and step 2 will be, we'll make it move. Okay. All right. So I'm going to call it here, and I hope you all have a great weekend. Stay safe, and we'll see you on Tuesday.
You too. Bye.
Bye.
You too. Bye.